Thank you for organizers and thank you for audience. Okay, hello everyone. I'm Hanwang, and today I'm very excited here to share our work, Visual Common Sense Representation Learning by Causal Inference. It's the light version of our main conference paper, Visual Common Sense RCN. In today's talk, I will firstly give a very brief introduction to the common sense definition in philosophy. Then I will go through the visual common sense in our CV community. After introducing some previous work on visual common sense learning, I will show the observational bias in nowadays CV models and how to solve it. Finally, I will present a toy experiment and give our proposed VC-RCN model. Okay, let's begin. So what is common sense? In the history of mankind, there are many philosophers trying to explain what is common sense. The first mover is Aristotle. He defines as the common sense as the ability to reach basic judgments. Up to now, there are still many philosophers trying to explain this abstract phrase. We can see, compared to the low-level vision tasks, high-level common sense reasoning are still elusive until now, even for us human philosophers, not to mention for machines. What is a visual common sense in our CV community? Actually, in our community, today's CV systems are very good at answering what, for example, classification, segmentation, and where, for example, detection, tracking. However, they are not good at answering why, which means asking for visual reasoning and high-level common sense reasons behind the machine's decisions. Our machine needs visual common sense to learn to answer why. In our work, we do not try to provide an exact definition for visual common sense. We just divide the phrase visual common sense into three natural parts: visual, common, and sense-making. By visual, first, we mean the large-scale visual source, and second, the unsupervised learning function without common sense label. By common, we mean the correlation. For example, given the tile, the robot can recognize it as a part of the car. Given sink, oven, microwave, refrigerator, the robot would know it is a scene of a kitchen. By sense-making, we mean the cognitive reasoning and affordance. For example, operating knife on the apple to get the sliced apple. We will know that the knife can be used for cutting. Seeing the cook pour the food into the plate, we can sum up that the plate can hold the food. However, visual common sense learning, especially sense-making, is still far from resolving. We can find many cognitive errors due to the lack of common sense. For example, in image captioning task, machine fails to describe the exact visual relationships, or generating the correct caption, but the underlying visual attention is not reasonable. In VQA, we can also observe the similar problem. Without visual common sense, model usually attends on incorrect object, even gives the right answer. Many previous researchers have tried to encode the visual common sense. The most direct way is supervised learning with a predefined visual common sense knowledge base. For example, Wisdom constructed a human-generated abstract scene dataset containing 213 relations annotated by AMT. However, these common sense relations need very expensive manual annotation. To solve this problem, weakly supervised learning comes. Actually, some previous work have performed weakly supervised learning from large-scale vision and language corpus. However, common sense is not always recorded in the text due to the reporting bias. For example, most may say people walking on the street, but few will point out people walking with legs. In fact, we humans naturally learn common sense in an unsupervised fashion by exploring this physical world. Can machine learn with visual common sense with unsupervised learning? A successful example is in our sister NLP community to learn word vectors. A word representation X is learned by predicting its contextual word Y, and finally used to encode common sense. For example, king minus man plus woman equals queen. How about vision? A few previous works have tried this pattern. such as contextual patch prediction, solving scope puzzles, and context encoder. But they are all far from effective in downstream tasks. The reason is that in NLP, common sense knowledges have already been recorded in discourse. In contrast, once an image has been taken, the explicit knowledge behind the contextualized objects will never be observed. The true common sense may be confounded by the superior observational bias with the correlation prediction. Oh, the bias comes. What is the observational bias? For example, given a large number of images containing both person and hot dogs, the machine may build superior correlations between the entity of person and hot dog, since they are commonly observed too many times. Then, in the downstream tasks, for example, in VQA, we ask, is the girl excited to have the hot dog? Machine may wrongly attribute the attention to the hot dog rather than the person, which leads to the cognitive errors and is not sense-making. How can we reach sense-making? Sense-making donates the unchanging truly cause for the existence of one object. For example, given object A to predict object B, what we are actually doing is to ask how likely would object A causes object B. That is, to learn the visual common sense about A causes B. The same can be applied to our CV community. Given a photo of person and toilet, when we predict the toilet given person, we are learning the visual common sense about person causes the existence of toilet. For example, person can use toilet. Vice versa, when the direction is reversed, we start to learn toilet can be used by person. In our real world, the situation can be different. There may exist many hidden evils that affect or cause either object A and B, what we call confounder, leading to the superior correlations. In our vision world, any contextual objects can become the confounder. For example, when calculating the causal effect about keyboard to mouse, the confounder set can be table, lamp, or computer. For the below image of person and hot dog, the confounder set can be table and plate. It's these contextual objects leading to the superior correlations. In this paper, we apply the causal intervention to eliminate the effects of confounder. As we introduced before, our visual world exists many confounders Z that cause either X or Y, leading to the superior correlation by only learning from the likelihood Py given X. The key insight of the causal intervention is to make a graph surgery that cuts off the causal link between Z and X. Then the Bayes rule is applied on the new graph. This process is called the do expression. Compared to the original equation, Z is no longer affected by X. The intervention forces X to incorporate every Z fairly, subject to its prior PZ. To further demonstrate the effectiveness of causal intervention in our CV community, we perform a toy MS-COCO experiment with ground truth object labels. We compare the difference between association Py given X and the causal intervention Py given do X. Here, we give a detailed analysis of the person and toilet. First, let's calculate the passive observation P person given toilet. That means, given a region of toilet, how likely there exists person. Here, we list a few images in the dataset. We can find that in the dataset, due to privacy, the image with both person and toilet can be very little. Therefore, P person given toilet can be low. When we conduct the causal intervention, the contextual bias is manually cut off. Any possible confounder Z would be fairly borrowed into this image according to a prior PZ. Finally, we sum up these partitions to get the final do results. We can observe that it becomes higher. Thanks to the intervention, we can increase Py given do X by borrowing non-local objects across the whole dataset to alleviate the observational bias. Based on this theory of causal intervention, we next present our framework, VCR-CNN. VCR-CNN takes an image as the input and generates the feature map from a CNN backbone. Unlike FastR-CNN, we discard the region proposal network here to directly use the ground truth bounding box to extract the object-level representations. Then, each ROI is fed into two branches. One is the self-predictor branch to predict its own class. The other is a context predictor with our do calculus. First, we maintain a pre-computed confounder dictionary Z, and each entry Z is the average ROI feature of the ith category in the dataset. Then, with the help of the confounder dictionary, we can compute the expectation of Z using attention and MvM approximation. This operation is a do expression in CV. Please note that it is quite different from the context-based models. With the help of the confounder Z, we actually borrow non-local objects, even not in this image, to help deconfounding. Finally, X and the expectation of Z would be combined to do the context object prediction. Our framework has three highlights. First, we combine the causal inference with unsupervised learning to study the visual common sense knowledge. Second, the design model is fast, light, and non-intrusive. By non-intrusive, we mean easy to use, just feature concatenation. Third, we achieved SOTA performance on 3 downstream tasks. Here, we show a part of experimental results. We can see concatenated on our VC feature. The models can receive huge performance improvements in all downstream tasks. We further visualize some qualitative experiments of utilizing our VC feature, the right one, compared with using pure object feature, the left one, in VQA and VCR tasks. We can see that with our VC feature, model can get more reasonable attention weight. To sum up, our community have already reached agreement that correlation not equal to the causality for a long time. However, few works have made great progress to use this truth into CV community. Here, we want to appeal that this golden truth deserves more attention now, and it still has a lot of potential waiting for us to exploit. That's all. Thank you.